Lab 4, Spring Mass in Motion. The objective of this lab was to observe the motion of a spring mass on a spring and analyze this motion to create a model with VPython using your understanding of Newton's laws and the energy principle to correctly model the motion. My project was successful because the motion of my model was almost directly correlated to the motion of the spring mass in the original video. These are some of the behind-the-scenes formulas that we used within the coding. First we see Hooke's laws, and then you see the formula for Ks, which is the spring constant in Hooke's law. I determined Ks based on the formula for the oscillatory period and the mass and stretch of the spring. Those further down are also the formulas for kinetic energy, spring potential energy, and gravitational potential energy. You'll see how they're factored into the lab later. When using Tracker, I determined the calibration stick based on the original length of the spring hanging with gravity, and also use the attachment point for the axes to determine the up and down motion of the spring. The first thing put into Python were the initial conditions. The mass of the ball, bot.m, was 0.402 kilograms. The ball position vector is below that, and the ball's initial velocity was 0. Below that, you can see where I inputted a CSV file containing the actual coordinates of the original spring mass as it rotated or bounced up and down. And so later you can see how we compared the two motions within the model. Here you see the while loop, where we define the initial energies and determine the gravitational force and the spring force and the net force to determine the new velocity, the new position, and the delta energies at after each delta t, which was 1/210 seconds. This was the code for the graph for plotting the change in different energies and the sum change in all energy at each time step. Here you can see the video. There's the code for the graph, and we scroll up and we see that the number of graphs or the number of lines on the graph are going to be 4 as indicated right there. And so now I'm going to run the program itself, run the module. On the left you can see the spring mass motion. The blue is the computer model, and the red ball is the actual motion of the original spring mass as determined by the CSV data file. Below on the right you can see the graph, and the red, you can see that the yellow, which is the sum of all the energies, is 0, or is close to 0. Next, to determine how closely the model followed that of the position of the ball, we plotted on the graph itself just the y change within the ball, and there you see me indicating the code on the left hand, and I changed the number of graphs to 2. So now we're running the model, and you see them again, but instead you see that the graph is just the y, graphing the y position, so we can actually determine how closely the spring mass or the model of the spring mass was to the ball. You see the ball is in red and the spring mass is in blue, and you see it's fairly close. The period might be, or the oscillation period determined might have been a little off, and you see that kind of changing at the end. Okay, first we can see that the energy principle is satisfied because the sum of all energies is equal to 0, or it's equal to a constant, and the sum of all energies within a system, there's no change because this is a bound system. And you can see that the red goes delta US, which is the spring force, and the delta K, which is the kinetic force, and the green, which is the delta gravitational force, all change, but their sum is always the same constant. And here you can see the comparison of the oscillation period. Okay, so here we compare the oscillation periods determined by 1, the x-axis from Tracker, and 2, the y from Tracker. And if you plot it within the system based on the Ks you determined based on the oscillation period of both, you see that it's closer for the oscillation period determined by the x-axis, and this is because for the y-axis there's an extra force that being that of gravity, and also which kind of affected the oscillation period, and consequently you can see the effects of that on accurately determining the spring force. Regardless of the small discrepancy, I think that my model did a very good job of modeling the motion as you noticed in the actual video.